All right. So welcome, everyone. It's my pleasure to introduce Kartik, who is assistant professor at IIT Chennai. So thanks, Kartik, for being here and telling us about your work. So Kartik has been doing some very interesting work on practical verification of distributed systems, and the floor is yours. Eager to hear what you have to present.
Thanks, Akash. Thanks for the introduction. And thank you for inviting me. It's a pleasure to give this talk. Feel free to ask any questions at any time during the talk as well. Happy to answer them. Right? So I will talk about some recent work that we have done on verifying correctness of what are called mergeable replicated data types. Yeah. Where are MRDTs used, right? One of the major use cases, right, of these replicated data types are for these applications like Amazon, right, Twitter or X as it is called now, and Wikipedia, which have users distributed all across the world, right? This is a major use case, right, for where you want to replicate data at multiple locations, right? Uh, for users who are distributed across the world, you want to give the same experience, right? In terms of latency, right? To load the web pages and so on. But for this purpose, I mean, you can't clearly place a server in just one location, right? Because if you place a server in one location, then clients in other locations, right, may face quite a reasonably high latency, right? So which doesn't result in the same user experience, right? So in order to make sure that all clients across the world see the same user experience, these applications typically have multiple servers, right? And users will interact with the servers that are closest to them, right? And this ensures that all users see the same experience, right? But now, I mean, so these applications operate on data that is continuously changing, right? So users make updates, let's say, to some Wikipedia page, right? Or they tweet something, right? In something. So there is data that's being constantly modified, right? And viewed, right? Concurrently at different locations across the world, right? So apart from the main benefit of replication, right, which is that it provides uniform low latency, there are also lots of other benefits, right? So it provides always on availability, which means that even if one server goes down, you can still reroute requests to other servers, right, and ensure that the application itself doesn't go down. It provides scalability, right? So you can add more servers as the clients increase, and it also provides fault tolerance, right? So you don't lose data. So the typical way, right, in which a client will interact with such a replicated system, right, is that so the client will issue a request to the nearest server, right, or replica, and then that replica will immediately reply to the client, right? Uh, so essentially, all the communication here is local, right, between the client and a single replica, and periodically these replicas will communicate with each other. And they will exchange their updates, right, to make sure that all the data across the replicas remains consistent, right, which means they actually are replicas, right, of the same data. Right? So that's the summary of this replicated systems model, right? So here you have multiple replicas of data, all of which are independently operated, right, independently accessed, potentially geo-distributed, but need not be geo-distributed as well, right? And it has many benefits, right? Fault tolerance, availability, and low latency, etc. Right? So the main question, right, that we want to sort of ask here is how to write applications for such replicated systems, right? How to write programs for such replicated systems, right? So traditionally, right, the approach that has been normally followed, right, is to sort of not make this replication explicit to the programmer, right? So the programmer, so it's the underlying system will ensure that actually there is no replication, right? So to a programmer, it will appear as if it's a single centralized system, right? Now, in order to achieve that, right, obviously, whenever you make an update at a replica, you need to synchronously send that update to all the other replicas, right? To make sure that there are no concurrent updates, right? There are no mismatches and so on, right? So this incurs a massive synchronization cost, right? So to give this image of a single centralized system is quite expensive, right? And that's something that we don't want to do, right? And that actually sort of negates many of the benefits of replicated systems. So what we're looking for is this so-called asynchronous replication model, right? Where uh, a user or a client, right, will only interact with their closest replica, and this replica will immediately serve the requests, right? And uh, in the backend, right? I mean, again, right? So periodically, these replicas will exchange their updates with each other, right? But this information or this particular exchange of information is not on the critical path. And this is where MRDTs, right, come into the picture, right? So MRDTs are a programming model, right, for programming replicated systems. And in the case of MRDTs, they make replication explicit, right, as part of the programming model itself, which means that as a programmer, right, you have to deal with the fact that, okay, there are multiple replicas, right? There are multiple copies of the data, right? And you have to deal with how to make sure that it remains consistent. Okay? So the way the MRDTs work is that they follow what's called this version control model of replication, right? Which means that whenever a client issues an operation, right? Whenever you perform an operation on a version, it creates a new version, right? It's like a functional model, right? So every time that you make an update, you create a new version. So there are always multiple versions floating around, right? For each replica, right, we'll look at the most recent version at that replica. Okay. So there could be multiple, so across replicas, there may be multiple versions, right? And now periodically, these versions at different replicas will be merged together to create a new merged version, right? So this merge is a new operation that also needs to be defined by the developer, right? And so this is what's called a three-way merge function, right? Which means it takes as input two concurrent versions. Okay, so and it also takes as input the least common answer, the least common ancestor between them, right? So this is basically the version, the most recent version from which these two concurrent versions diverged, right? Yes, there's a question, Akash.
Yes, so this is this version made available to the client? Can the client access any version?
No, so the client will always will only be able to see the most recent version at a given replica, right? Since the
Okay. The
client only
client doesn't
interacts
know
with
about
some
versions.
replica. Sorry?
So the client does not know about versions.
No, the client doesn't know about versions, but as a developer, you know that there are multiple versions, right?
Okay.
And
Okay.
you need to write this merge operation.
Thanks.
Right. Okay. So this three-way merge function merges these two concurrent versions v1 and v2 by also taking as input the least common ancestor, which is the most recent version from which these two concurrent versions diverged. So to fit this MRDT model, right, into the asynchronous replication model, right? So here, I mean, I have two clients, right, who are performing two operations, op1 and op2, right? Let's say at replicas R1 and R2, right? So now they have created new versions at, so we have new versions rather, right, at R1 and R2. And when these replicas exchange their updates, right, what is really happening is that you are merging the version, right, you're merging both these versions, right, at both replicas R1 and R2, right? So you will call this merge function with the two versions R1 and R2, and this merge functions will be called independently, right, at both the replicas. Okay. So let's take some simple examples, right, to make this more clear, right? So let's, for example, see a counter MRDT. Okay. So this MRDT is implementing a counter data type, right? So the value of a counter is some natural number, right? And it only supports one operation, right? So this is the operation that a client can perform, which is increment the counter. Okay. So a client can only increment the counter. So here's how an execution might proceed, right? So for example, I could have a version where the value of the counter is 5, and now a client issues an increment operation. So that creates a new version, which in this case is this version v1. Its value is 6 now. Okay. Concurrently, maybe at some other replica, right? Some other client, let's say, may issue another increment operation, which will then change the version. So it will also create another version, which in this case is v2. and its value will also be 5 plus 1, which is 6, right? So now I have these two versions, right? And now suppose these two replicas want to exchange their updates, right? So they will essentially call the merge function uh, for merging these two versions, okay? So the idea behind merge is that you want to preserve the updates that happened in each version, right? So I want to preserve both the increments, right? And I want to perform those increments now on the LCA, right? Which is the lowest common ancestor, right? Which in this case is 5. So the answer that I'm looking for is 7, right? So after I merge both these versions, I should get 7. Right? And one way to implement this is as follows, right? As shown, right? So this merge is a ternary function. So it takes as input the LCA V1 and V2. And I can implement this merge for the counter by essentially adding to the LCA V1 minus LCA and V2 minus LCA, right? So V1 minus LCA essentially counts the increments that happened in version V1, and V2 minus LCA counts the increments that happen in version V2. And then we add both those to LCA. So this will result in the total number of increments, right, that happened since LCA. So since the LCA version, right? And this accurately counts the increments that we wanted, right? So essentially it calculates the correct merged value. So to give another simple example, right? So here, for example, suppose at this replica 2, right, where we had this version V2, if the client issues another increment operation, then that version changes to, or the new version is created rather, with value 7, right? And now we may want to again merge, right, this new version with the older version, right, that was created by the original merge, right? So in this case, there is one more increment, right? So the value that we're looking for is 8, okay? And again, if you apply this merge function, but now the LCA will be the version V2, right? So we are merging both the 7s, right, with the LCA being 6, right, which is the version V2, and that will give you the answer as 8, okay? Okay, so let's take another example, right? So let's think about a set data type, right? So suppose we want to implement a set data type as an MRDT, right? So again, what are the operations, right? What is the state, right? So this is a simple set. So it maintains the contents of the set, right? So let's say I have some set of elements, right, which is E. Yes, there's a question, Dhruv.
Yeah, so in the expression where you have the LCA plus V1 minus LCA plus V2 minus LCA, which one, so it's not really clear whether the plus is commutative, because now it matters whether you first merge V1 minus LCA to LCA, or you merge V2 minus LCA to LCA. Like, do you have some comment on that? Because it will make a difference which one I merge first, right? Or will it not?
Okay, so
Because the order of
we are not
merging
merging. Okay, so we are
doesn't
merging.
matter.
So we are merging V1 and V2, right? So we are not merging V1 with LCA or V2 with LCA. But what you're maybe
isn't that
talking about is this algebraic expression. I mean, so here, I mean, plus commutes with subtraction, right? I mean, plus and minus commute with each other. So
plus and minus commute with each other? Okay, I see.
yeah. So
And
this is, I mean,
but
this is normal integer addition and subtraction, right? So yeah.
thing was, like, for the merge operation, we do need to know what LCA is, right? So it is a ternary application.
Yes. So the LCA is supposed to be provided by the system, right? So the system will maintain this version graph, and you can assume that the correct LCA will be provided. So given the correct LCA, are you able to compute the correct merge? Okay.
All right.
Yeah.
All right.
So what about reads, Kartik? If clients have to read, what happens?
Yeah, so reads don't change the state, so they don't create new versions, and essentially you'll just return the most recent version at that replica.
So it's not, it might be a stale value.
Yes, it might be a stale value. Yeah, so you're looking at the updates which reached that replica, right? So not all updates may have reached that replica. So we don't guarantee anything about the reads. Yes, there's a question from Rupa Shri.
Hi, Kartik. So I had one basic question. So how is MRDT actually different from CRDT, right? Like the original Shapiro paper, pretty much defines this as a PN counter, or rather because you're considering only an increment operation, it defines it only as increment, right? And the merge is considered to be the max of both the replicas, right? Is it that the merge function here is actually different? And although it is different, it is still commutative? Or basically, I'm trying to understand the difference, right?
Yeah,
Like the
so that
fundamental
is,
difference.
yeah. So state-based CRDTs are quite, and there is similarity with between MRDTs and state-based or CRDTs, right? Because they also use merge, but the system model is slightly different because so here you have this LCA, which is not available in CRDTs, right? So as we will see later, right? So in case of state-based CRDTs, you have to make sure all operations commute, which happens like for example for the counter, right? But as we will see in the next implementation, right, which is the set implementation, operations don't commute. So that is still fine with MRDTs. So MRDTs don't impose that requirement.
Okay, thanks.
Yeah. Okay. So for the set MRDT, we want to maintain this set of elements, which will be some subset of this set E. Okay. So that's why the state is the power set of E, right? So we'll maintain an element from the power set of E. And the two operations that we support, right, in general for any element of A, right, which belongs to E, is adding and removing the element, right? And this is the simple implementation, right? So if you want to add an element, you just take it union, right? And if you want to remove an element, you just subtract it from the current state. Okay, so this is the implementation of add and remove. Now here, add and remove don't commute with each other, right? So if you add first and then remove, then the element won't be present. But if you remove first and then add, then the element will be present, right? So this raises this issue, right? That suppose I had this common, let's say I had this LCA version, which was the empty set. And on one replica, if the client issued the add A operation, and on another replica, a client issued the remove A operation, right? So now what should the merge do, right? So should the element A be present or it should not be present? So here so here we rely on the developer to give the specification, right? Suppose the desired specification here is that add should win, right? Which means that whenever there are concurrent add and remove operations of the same element performed at different replicas, then when you merge these two versions together, you want to make sure that the element is still present in the merged version. Okay, so that's the desired specification that we want. And one way to achieve that desired specification, right, is maybe we define the merge function in this way, right? So here I take sigma L, right, which is the state of the LCA, right? And then I take sigma 1 minus sigma L and union sigma 2 minus sigma L, right? So sigma 1 minus sigma L will essentially be the set of elements which were added, right, in the version sigma 1, right? And sigma 2 minus sigma will be the set of versions which were, or set of elements which were added in the version sigma 2, right? So now this will make sure, right, that if you actually apply this this particular definition of merge on this example, right, then A is going to remain, right, in the merge. Okay. Right, but there is an issue with this particular implementation, right? Which is that you are not considering the effect of remove operations. So let's consider this particular execution, right? So here, suppose the original, so suppose the original LCA, right, had the element A, okay? And on one replica, suppose I removed A. And now I'm trying to merge these two versions, right? So I didn't make any changes in one version, right? In another version, I removed A. And now I'm trying to merge these two versions, okay? So now the remove should take effect, right? Because essentially there is a remove operation that was performed in one of the versions. So this element A should not be present after you merge, right? But if you apply our definition of merge, okay, then since A is present in sigma L itself, right? Therefore, it will continue to remain in the final merge version as well, okay? So we should consider the effect of or we should consider the fact that if an element is removed in one of the versions that are being merged, then that element should not remain in the merged version, right? Provided that it was not added concurrently, right, in another version. So this should ideally be the empty set, but it's not the empty set. Okay. So again, we can sort of correct this by changing our definition of merge. Okay. So suppose we changed the merge definition as shown in the slide, right? So which is that we consider the intersection of sigma L, sigma 1 and sigma 2, right? So when we consider the intersection, right, we are essentially considering the fact that whether or not an element was removed, right? So an element of sigma L, whether it was removed in one of the two versions, sigma 1 or sigma 2. Right? So if it was removed in one of the versions, then it won't be present in the intersection, right? And that means that we don't, and that is correct, right? Because we also don't want that element to be present in the merged version as well, right? And as usual, we take sigma 1 minus sigma L and sigma 2 minus sigma L because we also want to consider newly added elements, right? That were added in either of these two versions. Okay. So again, this seems like a correct definition, but again, even this does not work. Okay. And this, if we actually go back to our original execution, right, where I had concurrent add and remove, if you now try to apply this definition of merge on this particular execution, right? So here I have concurrent add and remove, right? So I want the add to win, okay? But since the element, so the element is present in the LCA, right? And it is being removed in one of the versions, so it won't be present in the intersection. But now it will also not be present in sigma 1 minus sigma L, right? So essentially, even though the element was already present in the LCA, it was added again in one of the versions, right? So that add should now take precedence, right? That add should reflect in the merged version, but it is not. It's not getting reflected here if you use this definition. So again, the way to resolve this is to add this timestamp, right? So every time we add the element again, we will essentially tag it with a timestamp, right? And we'll tag it with a unique timestamp. So in this case, let's say that the element was originally present in the LCA, right? So the set there contained a comma 1. Now when we add it again in one of the versions, we will add a new tagged value, right? Which is tagged with this with a unique timestamp, which in this case is 2, right? So we add a comma 2. Right, and when we remove it, we just remove all the versions, right? So that's the definition of add and remove now, right? So when you want to add an element, you will add a new tagged version of that element, and when you remove an element, you will remove all the tagged versions of that element. Okay. So now, if you use this new definition of add and remove with the definition of merge that we have developed so far, right? This will work now, right? Because sigma 1 minus sigma L, right, will basically contain the newly added version of that element, right, which is a comma 2. And a comma 1 will indeed be removed, right, because it was removed through the remove a operation, right? But one version of this element is still surviving, right, which means that the element a is still present in the final merged version. Yes, there's a question, Raghavan?
Yeah, I actually have two questions. One is when you say work or does not work, is it in who defines what is working and what is not working?
Yeah.
Now, I'll first let you answer that question. Then I have another question.
Yeah, so that's a good question. So we have not yet defined how to specify, right, what is it that we want. But in a way, right, so we want this add wins functionality, right? So which is that whenever there is a concurrent add and remove, then after you merge those versions together, the element should survive in the merged version, right? And that's the informal answer to that question. Right? Formally, I mean, we'll go through.
So you're saying basically the developer of this data structure has to define somehow what is the ideal output.
Yes, what should be the ideal output in case of concurrent updates, right? So if there are no concurrent updates, like in this particular execution, right, where there are no concurrent operations, so here it's as per the specification, right, of the usual set, a sequential specification, right, which is that if the element is removed, then it should not be present in the final version.
So do you want like some linearization of this, some serialized versions of these, any serialized version, any serialized sequence of operations? Is that enough?
Not necessarily. So,
but it has to be the result of some serialization.
Not necessarily. So we will see that. I mean, so there is a. I mean, there is a more sort of liberal specification that you can give, right? So for example, you'll see that in case of queues, right, I can actually dequeue an element multiple times, okay, which doesn't correspond to a serialized execution or a linearized execution. So here, I mean, we will see what
Sorry,
is
why
the exact
doesn't
execution
that,
time.
why is it not?
Yeah, so that depends on, so if the developer is fine with it, right? So in the sense that maybe the developer doesn't want the linearized specifications, right? They want some weaker specifications, which are still sort of important to them, right? But some properties may not be relevant, right? To the program. Maybe, yeah, ensuring linearizability may be too hard, right? Or it may not be even be possible for merge.
Okay, so you want a weaker spec.
Yeah, weaker spec. Yeah. So
Can I ask a question?
yeah, go ahead.
Okay, so actually it's not one but two questions. The first question is, if you are maintaining timestamps, they have to be global and not local, right? Because when
Yeah.
you're merging, it'll be merged against global timestamps.
Yeah.
But then this creates a problem because when you're there has to be a time synchronization all the time, which again increases the communication between all the servers, and
No,
that'll be
actually, yeah. So actually, there is a way to get unique timestamps without any synchronization. It's actually
how?
quite easy, right? So you can have unique replica identifiers, and you can use them, right? So every time, so in a replica, right? Let's say you keep a counter, and so you have this counter tagged with that replica identifier as the timestamp. So then it will be different across replicas.
Yeah, no, the
But there
problem
are
is
other
not.
ways to do it as well. I mean, there's Lamport timestamps. So there are protocols, right, which can ensure uniqueness of timestamps without synchronization.
No, so the thing is, like, we want the timestamps to be the same if the updates have been made at the same time, right?
No, there
Because
is
otherwise
no.
we replicate it
Okay, so
unnecessarily
maybe,
and there's a blow up.
So yeah, that's not true, right? So there is no notion of time here. There is no global time, right? Because each replica is essentially operating at its own pace, right? So yeah, there is no global notion of time. The timestamp, I mean, yeah, maybe it's not the right. So this is, I mean, this is what's traditionally used, right? But what by timestamp, what I mean is that
A unique
it's a
ID.
unique identifier. Yeah, that's what we want.
Okay, so it's okay if at the merge time there's unnecessary replication of data because of the creation of unique IDs.
Yeah, so here, in fact, there is a necessary replication because there could be multiple versions of the same element, right? So
All right.
it's not very efficient. Yeah.
Okay, and the second question is, why not just have this merge function give a maybe data type, which kind of like gives you a conflict, which is what we usually have. If there's a merge conflict, the local guy manually resolves the conflict, and in that way, we kind of prevent these kinds of conflicting merges between add and removes.
Yeah, but these are very basic data types, right? So imagine like hundreds of thousands of such operations, right? And how will you actually manually take care of each such conflict? So there could be hundreds of operations, right? Thousands of operations happening concurrently at like many replicas, right? And it's and here, I mean, you have a very fixed merge strategy, right? Or rather conflict resolution strategy, right? Which is that yeah, you just want, if there are concurrent adds and removes, then you want the add to win. So the question is, can we actually automatically resolve that conflict, right, using this conflict
All right.
resolution?
So there is a certain priority. Like if there are concurrent adds and removes, the add has to.
Yeah.
Okay, perfect. Cool. Thanks.
Ravan, do you still have a question?
Yeah, I had my old second question. So if along one branch from the least common ancestor, if I had a, let's say, a add followed by a remove, in the other branch, I only had a add.
Yeah.
So just maybe I'm asking a question of detail. What would be the ideal result in that case?
Yeah. So the semantics is that if an add is not visible, right, or is not cancelled out by remove on the same replica, then that add's effect should remain after merge. So in your case, the add in, let's say, the left replica, right, where there was a remove after it, should be cancelled out, but the other add, right, which was in the right replica, its effect should still remain after merge. So the merged version should contain element.
Okay.
Okay. Okay, so
So
this
you're
would
not
be,
giving priority to the ads here, right?
we are giving priority to the ads, right? Yes, we are saying that if there's a
Okay,
concurrent
but
ad
across replicas, you don't.
across replicas, so I mean, if on a single replica, if there's an ad followed by a remove, then
Okay.
that means that yeah, then we won't give priority to the ad, right? Only for concurrent add and remove, right, which happen across different replicas. Only then we will give priority to the ad.
Okay, but here in Raghavan's example, you're doing the remove in the left replica before
No,
the
so
add.
I think in the left replica, there's add followed by remove. So that cancels out that add at the left replica. And but in the right replica, there is an add. So in
But
which
why
case,
not have the two ads and then the final remove in the left replica?
yeah, but the desired conflict resolution strategy, right, is that if there's concurrent add and remove, add should be.
Only if it's concurrent.
Yeah, only if it's concurrent.
Okay.
So this slide just summarizes what we have seen so far, right, about this set implementation. So it's also called an observed remove set implementation. So essentially, if there are concurrent adds and removes, then you want add to win. And the implementation itself ensures this by tagging every element with a unique identifier, right? And essentially adding these tagged versions of an element to the state. Okay. So let's talk about specifications now, right? So how do you sort of, so the informal specification that we want out of this set, right, is that if there are concurrent adds and removes, add should win, but how do we formalize it? So one way to formalize it is to use this declarative sort of paradigm of specifications, right? So typically, so let me first just briefly define what is meant by declarative specification, right? So here I have a specification or a sequence of update operations of the data type, right? So you define a specification over a sequence of update operations, and the specification itself constrains the output of a read operation, which occurs after this sequence. Okay. So for example, here is how I would define or how I would define the specification of a sequential set, right? So here I'm talking about a sequential set implementation. So let's say if I have a sequence of set operations, right, which I have denoted here by this pi, right, which is O1, O2 up to ON, right? So each of these OIs are some add and remove operations, right? So this is a sequential set, right? So there's no merge, there is only one replica, right? You can think it like that way, right? Now, if this sequence of operations leads to a state sigma, right, then you want to constrain what is present in the state sigma using this sequence, right? So I can say that, for example, sigma contains some element A, right? If and only if pi contains an add A operation that is not followed by a remove A operation. Okay. So if A is present in sigma, then there has to be an add A operation in pi, right? And it
So
should
you're
be followed
assuming
by,
that you start from the empty set, is it?
yes, assuming that we are starting from the empty set. Yeah. So assuming that we are starting from the empty set, we apply the sequence of operations on an empty set, right? And then this element A will be present if and only if pi contains an add A operation, which is not followed by a remove A operation. Okay. So this succinctly sort of defines all possible behaviors, right, of a sequential set. Okay. So let's try to now sort of modify this particular spec, right, and try to inject this conflict resolution strategy that we have. Okay. So what we want, right, is that if there are concurrent adds and removes, right, then after you merge, the output, the merged version should rather contain this set A, contain the element A. Okay. So now we no longer have a sequence of operations, right? Because there are multiple replicas, right? And on each replica, you are performing operations, right? So there is no sequence, there is no global time, right? So instead, what we have are sets of operations, right? So I'll call each operation as an event, right? So we have a set of events which are denoted by the set E, right? Which is O1, O2 up to ON, right? So now it's just a set of events. Each event corresponds to an instance of an operation. Okay. in addition, we also have some more information, which is this visibility relation, right? So we know which operations happened on the same replica and which operations happened on other replicas, right? On distant replicas, right? So this information is captured using the visibility relation. Okay. So if two operations happen on the same replica, then they will be related by the visibility relation. Otherwise, they won't be related. Okay. And now I can now modify this sequential set specification by saying that sigma contains the element A. If and only if this set E, right, it contains an add A event that was not visible to a remove A event. Okay.
So, sorry, what is the visibility relation? Is it a total order on the?
No, so yeah, I'll just define it in the next slide, but informally it's a partial order, right? So events on the same replica will be related by the visibility relation. But
So
events
that will be a total order.
Yeah, so on the same replica, it will be a total order. But since we're
Okay.
considering all events, right, across the entire execution, which means we also consider events across replicas, they won't be related by the visibility relation, right? So now if an add A event is not visible to a remove A event, right, which means that these events actually happen concurrently on different replicas, right? Then the element A should be present in the final state, right? Otherwise, it should not be present, right? So if an add A event is visible to a remove event, then it should then the element should not be present. Yes, question, Raghav.
So this is an alternative to using those timestamps, is it? This visibility thing.
No. So the timestamp was an implementation specific thing, right? So that's how we implement OR set. Here we are talking about how to specify OR set. So this is only about specification.
Okay.
Okay, so let's clarify this visibility relation, right? So if you have events which are nothing but operation instances which happen on the same replica, right? Then so here, for example, I have E1, right? This event E1, let's say which happened on one replica, and later on the event E2 happened on the same replica. Then I have E1 visible to E2. There is also another way we can get visibility, right? So for example, here I have this operation E1 or this event E1, right? Which happened at a replica, which was then merged, right, with another replica. And then on that merged version, I performed another operation, right? So in this case as well, this event E2 was performed on the merged version, which means it contains the effect of the version E1, right? So therefore, in this case as well, we will say that E1 is visible to E2. Okay, so these are the only two ways in which you can get visibility, right? Visibility is a transitive relation. Okay. So now this means that if you have events which happen on different replicas, right, then they will not be related by the visibility relation, right? So if E1 and E2 are concurrent, right, then neither E1 will be visible to E2 nor E2 will be visible to E1. And the specification that we just discussed on the last slide, it will make sure that if an add is not visible to a remove, then the add will take effect. Yes, this is a question.
Yeah.
Sorry. Yeah, sorry, go ahead.
I had this question. So, is it that,
Actually, your voice is breaking a lot. Can you try again?
is it better now?
Yes, it's better.
Okay. So, I had a question, right? Is it that a remove
Oh, it's
on
it's still breaking. Maybe you can
event?
type it
Otherwise,
out.
what would remove event have been?
I couldn't get the question.
Rupashri, I think you could type the question in the chat and he'll answer it asynchronously.
So the question is, will the remove event precede an add event? What does that mean? So if are you talking about events happening on the same replica? So if you remove an add happen on the same replica, then I mean this is up to the client, right? So the client can issue remove and add events in any order. right, at any replica. Because if replica R1 got removed and replica R2 add, then would there be visibility of remove on R1? So visibility is a relation over events, right? So if you performed remove operation on, let's say, R1 and add operation on R2 concurrently, yeah, so in that case, no, so only after you merge them, right? So after you merge both R1 and R2, and then if you perform other operations later on, right, on R2, then yes, remove will be visible to those operations. So that's clear from this figure as well, right? Where I have this E1, right, which is performed on a replica and then later on merged with another replica. And now of that merged version, if I perform E2, then E1 is visible to E2.
So, Kartik, this
Yeah.
concurrent, this is a definition of concurrent, right? That two events are concurrent
Yes.
if
Yes.
neither is neither happens before the other.
Yeah. This is the definition of concurrent. Yeah, Raghu.
Kartik, this definition you're giving now, it's kind of, is it general across all MRDTs or the
Yes.
set-based thing that you gave in the previous slide, I think?
No,
Or is
yeah.
it only for the set data structure?
No, this is general, right? So visibility relation is general.
Visibility is general, and also will you also say how to use the visibility relation to do the merge?
No, so that is specific to the data type, right? So the way merge, I mean set data type uses this information, right, about concurrency.
Okay.
So yeah.
So can you remind us what is the use of this visibility relation? Where does it come to play?
Yeah. So here, right? So we modified the sequential specification of set, right, by saying that what we want is the state, right? Sigma should contain an element A if and only if the set of events, right, E contains an add A event which is not visible to a remove A event. Right? So which means that the remove A should have happened concurrent with an add A.
Okay, but this statement is only about sets. But is there a general statement for all MRDDs that uses the visibility relation?
No, I mean, so the fact is that, I mean, you can write specifications which use this visibility relation. Now, different data types may want to use the visibility relation in different ways. Right? So visibility relation gives you a way of specifying what are concurrent operations and which operations are not concurrent.
Okay. And when you say set of events on the left side, so all the specification of any MRDD would want to work on a set of events. Is it correct? And not a sequence.
Set of events with visibility relation. Yes. So
That is the general template.
Yeah. So that's what I'm defining. So I'll define this in the next slide itself, right? Yeah. So to write specifications, we use this so-called abstract state, right? So the abstract state is just a set of events E, right, along with some information about these events, right? So what are the operations? What are the return values, right? What is the timestamp, right, or the identifier of the event? And right. So now I can write specification over this abstract state. Okay. And so, for example, the specification of the OR set, right? This is just what we had discussed currently, right? So, which is that. So this OR set specification, which is denoted by this FOR set, it constrains the value of the read operation, right, on a given abstract state, right? And it says that the read operation should return the element A only if on that abstract state there was an add operation, right, and a remove operation was not visible, right? So the add operation was not visible to the remove operation. Right? So there exists this event E, which is an add event, and there doesn't exist this event F, which is a remove event, such that E is visible to F. Right? So only those elements A should be present in the output of read operation. Right? So this is so in general, different data types would write the specifications in different ways, right? But they have access to this abstract state. So then we have this classical problem, right, where on one side we have the implementation, which uses this timestamps, right, and this definition of merge, right, using intersection and difference and so on. And on the other side, I have the specification. Now, so does the implementation satisfy the specification, right? That's the first question. And now the second question is, does the implementation ensure convergence as well, right? Which means if you have different replicas, right, will all the replicas eventually reach the same state, right? After all the events have been processed by all the replicas, right? So essentially what we're asking is, if two replicas which have witnessed the same set of events, right, will they have the same state or not? So in our work, we have basically come up with a verification procedure for showing functional correctness and convergence of MRDTs. Okay. So the specification here is the declarative specification that I've just discussed. Okay. And we mechanize and automate this verification process using FSTAR. And we also proposed a weaker notion of convergence modulo observable behavior, which permits more efficient MRDT implementations. And we have built a library of various data types, right, such as sets we already seen, maps, queues, flags, counters, and so on. Okay. So let me just briefly discuss the main concept, right, behind this verification procedure, right? So the main idea is to use this so-called simulation relation, right, a replication-aware simulation relation. So this is just a relation which links the abstract state, right, which consists of this events and visibility order, with the actual concrete state sigma as maintained by the implementation, right? So this RSIM is something that we expect the developer to write. Okay. And this RSIM, so given this RSIM, we then verify whether this RSIM is correct or not, right? So we show that RSIM holds in all executions in an inductive fashion, right? Which means that in every execution, for any state, right, for any concrete and abstract state, they are related by this RSIM relation. And we also show that this RSIM is sufficient enough to discharge the specification, right, of the data type, as well as the convergence requirements. So in the step one, we show that this RSIM holds inductively. Yes.
So Kartik, the abstract state is the set of events seen along with the visibility among them. Is it? Is that?
Yes. Yes.
Is that exactly the abstract state?
Yes, that's the abstract state.
Okay, thanks.
Yeah. Right. So this RSIM, we show that it holds inductively at every step in every execution, right? So inductively means that we consider only single steps of the execution, right? So one of the steps would be, for example, an operation of the data type, right? So if I consider two states, right? So if I consider the abstract state I and the concrete state sigma, some arbitrary states I and sigma, which are related by RSIM, then if I perform an operation of the data type, right? So if I perform the operation both on the abstract state and on the concrete state, right? So when I perform on the concrete state, I'm going to use the implementation. But when I'm performing on the abstract state, this I prime will essentially contain a new event, right, corresponding to that particular operation, right, along with the changes in the visibility relation and so on. Okay. So now, if I and sigma were related by RSIM, then we ask whether or not I prime and sigma prime are also will they also continue to remain related by RSIM. Okay. And the second major operation is the merge operation, right? So here I essentially want to consider the merge happening in both the concrete and the abstract state, right? So I have these three. So since merge is a ternary function, right? So I have three abstract states and three concrete states now, right? So there's sigma LCA, sigma A, and sigma B. And then I have their corresponding abstract states, right? And now if these three pairs of abstract and concrete states, if they are related to each other by RSIM, then after I perform a merge, right, in both the abstract and the concrete domains, right, will these states continue to remain related by RSIM? Right? So this is what we formulate queries, right, which correspond to these two checks. Okay. And now if these two checks are satisfied, right, then we ask whether or not RSIM is sufficient to prove specification and convergence, right? So essentially, for verifying specification, we take some arbitrary I and sigma, which are related by RSIM, and then we essentially apply the specification, right, which is this function f, right, for some read operation OP, right? And let's say if it gives the return value v, then we ask whether or not by performing the same operation OP, but on the concrete state, right, which is sigma, do we get the same return value? Okay. And for convergence, we check whether or not are there two different concrete states which are related to the same abstract state through RSEM, right? So if this happens, right, then essentially you won't get convergence, right? But if there is only a unique concrete state, right, which is related to an abstract state, then convergence is guaranteed.
Kartik,
Yes.
just a quick time check.
Yeah.
I mean, so we actually don't impose a hard stop at 1 hour. But I think it'll be good if you can let people know how long you plan the talk for.
Yeah. So so I'm almost maybe around 75% done. Yeah. So
Okay.
Yeah. Maybe I'll require maybe 10 more minutes.
Okay. All right.
Yeah. So this is just an example of the simulation relation for the OR set that we had discussed, right? So this relates the abstract state and the concrete state, right? And the concrete state contains these pairs, or rather, the concrete state is a set of these tuples, right, of the form A, T, right? So these are versioned elements, right? So we'll say that some versioned element A, T is present in the concrete state if and only if there was an add A operation, right, with the same timestamp and T, but that was not visible to a remove A operation. Right? So this simulation relation is actually very similar to the declarative specification that we wrote for OR set. But in general, I mean, this is not always the case, right? So the simulation relation can be much complicated than the specification.
Kartik, there's a question.
Yeah. Yes.
Hi, Kartik.
Yeah.
Yeah, can you hear me?
Yeah, I can hear you.
Yeah. So my question is I and sigma, is I a global set and is sigma a global state, or is it per replica?
No, so these are some arbitrary I and sigma, right? So they could be, so there's no global thing as such, right? I mean,
Okay,
sigma is a state at some replica, right? And I is the abstract state, essentially at that replica itself, right? So
I see.
so we are doing this per replica, right? And
Okay.
but these states could be, these are arbitrary, right? So they may have been, yeah, they could be reachable through some arbitrary execution, right?
Understood.
Okay.
Okay, thank you.
So in addition, we also assume some store properties, right? Like the fact that we have increasing timestamps, right? So if two events are related by the visibility order, then the timestamps are increasing, right? And timestamps are unique as well, right? So two events don't have the same timestamp. And we also assume something about the LCA, right? So we mentioned that this LCA is the most recent version from which both versions diverged, right? So we formally, I mean, encode that property by saying that the events in the LCA are present in both the branches, right? So it's the intersection of the events in both the branches, right? And they must have the same visibility relation, right? So those events should have the same visibility relation. So yeah, these are just some of the results that we got. So we basically verified a bunch of MRDTs, right? And given the, so we expect the simulation relation to be written by the developer, but even after having that as input, right, in some cases we are not able to automatically prove that the simulation relation was correct, right? Which means the 4 checks that I just mentioned, right? So for that, we had to manually write some lemmas in order to prove those. So I'll just briefly discuss some of the issues with this work, right? So first is that it is hard to write or even interpret the specifications, right? So for example, this is the specification for the QMRDT that we had, right? So it has a bunch of axioms, right, which are essentially encoding this Q semantics, right? The first in, first out, and so on. But I mean, this is not very easy to interpret, right? So in fact, this corresponds to this at least once DQ semantics, right? Where you can DQ the same element multiple times, right? But it's not obvious or apparent at all by looking at the specification, right? And the other issue is that verification requires this replication aware simulation relation, right? Which is very hard to write in some cases. Okay. So now we want to sort of consider another way of specifying, right, which is to use linearizability, right, for MRDTs, right? So instead of having a declarative axiomatic specification, right, why not we just say that the state at every replica should be a linearization, right, of the events at that replica. Right? So instead of using full-fledged specification, we just want to use the conflict resolution policy, right? So this is the only thing that we expect from the developer, right? Which is that for non-commutative operations, right? If they are concurrent, what should be the conflict resolution policy? Okay. So this is expressed as a binary relation, right? Which we call as this RC relation over non-commutative operations, right? So for example, for the OR set, the RC relation will just be the set of will be the set of tuples, right? Remove A followed by add A, right? So this is saying that if you have concurrent remove A and add A operations, or remove and add operations of the same element, then you will order remove before add. So this is the only input that we expect as part of the specification, right? So and now our correctness, right, our correctness criterion is that each replica state should be a linearization of the events witnessed at that replica. But additionally, we also want this linearization to satisfy certain properties, right? So which is that the linearization between two events should remain the same in all replicas, right? So the same two events, right, may appear in different replicas, right, through merges, right? And now the linearization order between them should always remain the same. We also want this linearization order to obey the conflict resolution policy and the visibility order, right, which is the local ordering, right, of operations within a single replica, right? So I'm skipping some details here, right? So we don't actually enforce RC subset of LO, right? Because it may not be always feasible to enforce RC ordering, right? But this is the general gist, right, of the desirable properties that we want the linearization order to follow. So let's just take a simple example, right? So let's say, so given the OR set, right, which has this conflict resolution policy, okay, if we consider this execution, right, where I have remove and add of the same element on two different replicas, when I merge them together, right, my correctness criteria now is that the merged version should be a linearization of these two events, right? So in this case, my conflict resolution policy says that remove should occur before add. Remove is the event E1 and add is the event E2, right? So therefore, the linearization should be E2 of E1 of sigma L, right? So this is what I want the merged version should to be, right? So we essentially need to show that the output of merge, right, is actually this particular linearization. Okay. So the way that we show linearizability is that we prove some algebraic properties of the merge operation, right? So we essentially show that this merge commutes with operation application, right? Which means that, so if I have this merge, right, that is performed on these inputs, right, where the LCA is sigma L, and let's say the two branches to be merged or the two versions to be merged are E1 of sigma 1 and E2 of sigma 2, okay? Now, if I want E2 to be linearized earlier, right, or before even, right, then in this case, I should be able to say that this application of E2, it commutes with the application of merge, right? Which means that I can peel off E2, right, from this third argument, right, of merge and apply it first, okay? And then continue with the rest of the merge, okay? So this is commutativity of merge and operation application, right? So if E1 and E2 commute with each other, then either one can be peeled off, right? But we only peel off one operation, right, appearing in one of the versions, okay? Otherwise, we use the RC to decide, right? So if, for example, E1 is a remove operation and E2 is an add operation, then I will use RC to decide that, okay, I should peel off E2 first. Next, we require merge itself to commute, right? Which means that merge of sigma L, sigma 1, sigma 2 should be merge of sigma L, sigma 2, sigma 1. Okay. And this allows the application of property 1 on both the replica states, right? So essentially, if I peeled off all operations on one replica, I can then swap the two replicas together, right? And then peel off operations on the other replica. And finally, I require this idempotence of merge, right? Which is that merge of sigma L, sigma L, sigma L is a sigma L. So let's see how, I mean, I can use, if I have these three properties, right, then I can linearize this particular example in the correct manner, right? So I have this merge sigma L, sigma E1 of sigma L and E2 of sigma L, right? So now I can use commutativity of merge and operation application to bring out E2 outside, right? And then I can use it again, right, to bring out E1. And finally, I use the merge idempotence to show that this merge sigma L is sigma L, right? So in general, I mean, if you can prove these three properties, right, then you can show linearization, right? for any arbitrary MRDT. So the next question becomes how do we actually verify this algebraic properties, right, of merge? Okay. So so in general, I mean, it's not easy to verify commutativity, right? And in particular, for right. So there was a question on the chat, I guess, sometime back. Didn't notice it. Yeah. Okay, I think I already answered that. Yeah. So suppose let's say we want to prove this particular algebraic property that merge and operation application commute with each other. In the case of, let's say, the OR set, right? So here this E2, right, is actually an add operation, right? Because the resolve conflict policy, right, the conflict resolution policy, it will order remove before adds, right? So we want to show that merge and E2 commute with each other. But if you look at the OR set definition, right? So the way add is defined, it actually uses set union, but merge uses this set intersection and set difference, right? So it is known that, I mean, set union and set difference don't commute with each other, right? So if you, for example, perform union first and then difference, right? Then it doesn't give the same output as performing difference first and then union, which is essentially what you are trying to prove, right? When you want to prove that add operation commutes with the merge operation, right? Because the merge performs set difference, but the add performs set union, right? But set union and set difference don't always commute with each other, right? So in fact, in this case, if you want to show, right, that this merge and add operation commute with each other, we need this specific property, right, which is that essentially this S2 intersection S3 should be empty, right? Or in this case, should not be empty. So in this case, it means that this element A comma T that is being added by the add operation, it should not be present in the LCA version, right, which is sigma L. Okay. So this property is very specific to the OR set, right? But it can be derived using two other properties, which is uniqueness of timestamps and this property that any tuple A comma T in sigma L must have been the result of applying an add A operation with timestamp T, right? So what we want to do is we want to avoid this kind of MRDT specific properties, right? Uniqueness of timestamps is a system property, but we want to avoid using any such MRDT specific properties, okay? So for that, what we propose is we can automatically verify these algebraic properties using induction on event sequences, right? So essentially, in order to prove these algebraic properties, right, it's not so straightforward to do it directly, right? Because we need to relate, right, this the states that are obtained with the events that led to that state, okay? But alternately, we can use induction on the set of events which led to the state, right? So here, for example, right, I had these three states, sigma L, sigma 1, and sigma 2, right? So the sigma L would have been obtained by performing some linearization, right, or some sequence of events pi L, let's say on the initial state sigma 0. And similarly, the sigma 1 and sigma 2 would have been obtained by performing some sequence of events pi 1 and pi 2, right? So now I can use induction over these sequences to show that this required algebraic property holds, okay? So we perform this algebraic property by performing three separate inductions on the three event sequences, right, which is pi L, pi 1, and pi 2. Right, so this is just so briefly I will just explain the induction on pi L, right? So here in the base case, I will essentially assume that pi L is empty, right, which means that I'm performing the operations on the initial state itself, right? So sigma L is sigma 0, which recall is the empty state, right? So in the empty state, I can directly discharge this this particular algebraic property. And for the inductive case, I assume that it holds, right? That the commutativity property holds for some arbitrary sigma L, right? And then I try to show that it continues to hold if I add one more event, right, on the sigma L, right? So this event E is being added not just on sigma L, but on all the on the two branches as well, okay? So if I can show that this is the case, then that means that for any arbitrary sequence pi L, which leads to the LCA state, this property will hold, right? And then I can also show, so separately I can do the induction on the other two branches as well. Okay. So this only requires uniqueness of timestamp, right? So we don't require any MRDT specific property to discharge this algebraic property that we require. So this is ongoing work. So we have a few more algebraic properties that are required to construct the correct linearization sequence. So we don't, so aside from the 3 properties that I mentioned, we require a few more. So we have some very positive results. So we have been able to automatically verify linearizability of all the MRDT implementations from the previous work. And in addition, we also discovered some buggy MRDTs, right? And we repaired them, and we also verified the repaired versions. So currently we are working on verifying more complex MRDTs. Right. So sorry for taking a bit more time. So with that, I'm going to conclude now. So in this talk, we saw, I mean, 2 different specification verification approaches, right, for MRDT implementations. So the first one was this very declarative, I mean, this declarative axiomatic approach, right, where we specify correctness using a set of axioms, right, considering the return value. And so it can lead to very expressive specifications. But the sort of flip side is that the specifications are hard to parse and also requires the simulation relation as input for verification, right? So next we looked at this linearizability and conflict resolution policy as the spec, right? So it's a very simple spec, okay? And it also enables automated verification through induction, but at the same time, it's not as expressive, right, as the declarative spec. So for example, I cannot express things like at least once DQ semantics, right, for Q, or semantics which are weaker than the sequential spec, right, using linearizability. So in the future, I mean, we could look at, for example, enriching the specification language even for linearization, right? Maybe allow some weaker specification, right? And also improving automation, right, for more complex MRDTs. Right. So with that, I'll conclude. Thank you all for listening. Happy to answer questions.
Thanks, Kartik. Any questions? Any final questions?
So, Kartik, yeah, the second work is very interesting. Nice and clean specification, a nice proof technique.
Yeah.
But so I was just wondering, what is the,
Hmm.
I mean, are the 2 ways of specifying related? Is one stronger than the other, or the 2
I mean,
kinds of specifications you gave?
yeah, so you can, I mean, you can always translate from one to the other, right? So you can translate, for example, and this linearizability based spec to a declarative spec, but declarative specs in general could be weaker, right, than linearizability. So you may not be able to get an equivalent linearizable spec for a
But this,
declarative
the
spec.
second one certainly seems more useful. I mean,
So at least for all the real world scenarios, right, where you're only interested in this conflict resolution policy. Right? So otherwise, you just want linearizable spec anyway. Okay.
All right. If there are no more questions, let's thank Kartik again. Thank you so much.
Thanks. Thanks.
Okay. Bye, everyone.
Bye.
Bye.